Hello, everybody. Welcome to our first, this is actually our second, but it's going to be our first Exoplanet Hangout that's going to be held on our new time, which is Wednesday evenings at 7 o'clock Eastern Time. I'm hoping this is a good time for a lot of you. My name is Tony Darnell. I'm from deepastronomy.com, and today we're going to be talking about life on some of the closest exoplanets to the Earth. And we're going to talk about what some of the properties of some of these planetary systems are, as well as what conditions might be needed for life to arise on some of these worlds. And some of them you've heard about. We're going to be talking about TRAPPIST-1 and Proxima Centauri b, and lots of other worlds that are in the area, as well as any that you'd like to hear about. I hope that if you will, we're broadcasting right now on 3 different social media platforms. I'm on YouTube, Twitter, and Twitch. And I'm hoping that as you are watching on each of these platforms that you might interact and ask us some questions, because I have with me these Hangouts are a collaboration between the Planets Foundation and Deep Astronomy, where every single week we want to bring these to you and talk to you about the science of exoplanets. Because if you think about it, folks, this is brand new stuff. I mean, 25 years ago, nobody was talking about exoplanets because we didn't even know there were any. We didn't even know there were planets around other stars. And so now the field has exploded. Not only do we know there are other planets around other stars, but there are more stars in the Milky Way galaxy than there are There are more planets in the Milky Way galaxy than there are stars. Switch that around. I'm going to have to get used to this new time slot myself. So anyway, to me, it's an astonishing thing. And a lot of people will say, well, you know what? If there's so many exoplanets out there, surely we can't be alone. And I'm sorry, but the jury's still out on that. We don't know for sure if that is the case. We have not seen any evidence of life anywhere else but on our blue planet. So I don't know. We're going to have to keep looking, and that's what we're going to be talking about today. What are we hoping to find in some of these, and why are we looking in some of the closer planets, and why not look at some farther away and say 50,000 light years away? And we're going to be talking mostly about the ones that are covered in the Planets Foundation. They have this thing we talked about last week called an exocube, and we're going to be talking about and it has a map in there of the 50 closest exoplanets, and so we're going to be talking about those here today. Now, there are several ways you can interact with us, but I'm looking directly at the YouTube live chat, and I'm already seeing, so Yurik Mazino is already on there, and Michael Jobin is there, and some people whom I have not seen before, which is good, because I'm hoping to get this time slot for different viewers than people who might have seen the 3 o'clock Thursday Hangouts. Those are still going on, by the way. This is in addition to those Hangouts. So, well, I will get to your questions and comments. Also, Kevin is going to help me. He's looking at the other platforms, and we're going to be checking in with him as well. So we are waiting on one of our guests, but I will go ahead and introduce the one that is here. I'm with Dr. Svetlana Berdugina. She was here. She was with us last week. So welcome, Svetlana. It's good to see you again.
Thank you, Tony. Thank you for having us. Nice to be here.
It's my pleasure. And I want to, you were with us last week talking a lot about this really amazing algorithm that we had, where you guys were trying to look at variations of light and to be able to map the surfaces of planets. And I'm still thinking about that algorithm. It's just amazing to me. So we're hoping with the Planets Foundation, right? And you can correct me on anything that I say incorrectly here, but the Planets Foundation is hoping to build a set of telescopes that is not only going to be able to help us characterize these exoplanets, but actually search for life as well. Is that true?
Yeah, exactly. We design and want to build a telescopes which are totally dedicated to exoplanetary research and exoplanetary follow-up, because we have smaller telescopes to discover them, but as it comes to learn about them, what are the atmospheres, what is on the surface, and if there is life, we need much bigger telescopes. And this is what the main goal of Planets Foundation, to build such dedicated instruments. And everybody who wants to join us, please do that.
So how can people get involved? Let's go ahead and talk about that first.
Okay, so we have projects right now going on. Planets Telescope is called. This is which gave name for our foundation. This Planets Telescope is under construction in Haleakala and in Maui, and we are looking for primary support is a monetary support. So on Kickstarter, we have a campaign. Everybody who wants to have their name on the telescope, please donate us money or buy Exocube. One thing. Other thing, if you have particular skills as an engineer or software engineer, we'll have a job for you later on as we come to operate it and close to completion.
And do you have a timeline now for some of these things yet?
Right. We plan to have a first light in less than 2 years.
Yeah, that's right. Because the objective, we talked about this. Excuse me. We talked about this a little last week, folks, and also in another hangout prior to that, where there are links in the description box. So check out some of the overview of what the Planets Foundation is doing. We don't want to get into that too much here, but these guys are. It's an extremely, I think, important effort to get to not only just raise awareness and to get the telescopes built, but also to give us never before available tools to search for life in the universe. And so, okay, so it looks like my other guest is here. Let me just double check here, Jeff. So, are you there?
I am.
I'm
right behind you.
And we can hear you, too, so that's good. This is Dr. Jeff Kuhn, except we're only looking at half of your face. I wonder if you might move your camera down just a bit. And
I see.
Are you there? Yeah. It's fun. We're looking at your nose. You look like that little Kilgore guy with your nose sticking up. But
that's interesting. My camera shows my whole beautiful face.
Okay, well,
how can you only part of my face?
Well, we're not seeing your whole beautiful face, Jeff. I'm sorry. There you go. That's better. Now we can see your mouth. But your connection isn't very good. Are you on wireless?
I am on the only connection I'm able to manage.
Oh, okay. Well, then we'll just have to make do. If you might speak up a little bit, because you're a little bit low on your volume as well, so that would be helpful. So this is for those of you who don't know, this is Dr. Jeff Kuhn. He is also a member of the Planets Foundation, and if I put the lower third up, I cut his face off entirely. So I'm not going to do that. Anyway, so Jeff, we're getting ready to get started here. I've got a lot of people showing up here looking at the live chat. I've got a couple of questions, but we're going to be why don't you give us a background first of all, guys? And I'm not sure which one to go first. It could either be Svetlana or Jeff. Let's talk first about what we mean by a habitable exoplanet.
Yeah, I can start.
Okay.
So, sure, as you mentioned, we have this little blue planet where we live, and this is, from science point of view, this is one data point. Habitable planet, the one we have. So we are trying to understand what's habitability, and we look at ourselves and say, okay, we need water, we need oxygen, we need sunlight. These are three important components. On top of this is food chain is built, many levels of life that can support each other. And what is the result of our activity? We produce methane, we produce carbon dioxide, or vice versa. Life produces oxygen, and it's kind of a living planet. So we take those features and we think like, okay, if this is one data point, can we define somehow habitability based on that? And this is how we do. We say, well, it seems like in the solar system, it's the only planet which has life and has oceans on the surface. So why not? This is the main criteria. So we put it as a first primary criteria for habitability: water, liquid water on the surface. This requires a certain temperature on the surface, means distance from the star, and presence of the atmosphere. So these are two very important conditions that we search for. So often you hear about detecting potentially habitable planet. That means that it has a potential to have ocean on the surface if there is the atmosphere, and the temperature of the surface is similar to what we have here.
Okay, I want to go back to this because I get a lot of comments on this idea of one of the things that we're looking for is liquid water. Can liquid water be present on all these planets? And whenever we figure out that the conditions are such that yes, in fact, you can have liquid water, we get really super excited. But a lot of people say, aren't we limiting ourselves? Why do we do that? Why do we limit ourselves to, first of all, having liquid water? What's so important about that?
Well, it's a very nice molecule. You know, I work with
nice molecule.
It's one of the best molecules you can imagine for life. So first of all, water is made of hydrogen and oxygen. Hydrogen is the most abundant element. Oxygen is one of the most abundant. And second abundant is helium. It makes no chemical connection. So you take hydrogen and oxygen, which are most abundant. You make second most abundant molecule in the universe is water, or third maybe, but still very abundant. You find it everywhere. So what's good about it? It's like a triangle, you know, like this. So the molecule, we said 109 degrees angle here, and so it bonds us like this, yeah, and like doing things like this, and you know, it's a nice molecule. It's a living molecule, and it has like on this top, it has a charge, negative charge, and in the ends it has positive charges. And when this kind of charged molecule moves around, it starts to connect to all other charges, like with water molecule or other molecules, and that makes it perfect solvent, what we call it. So it can attach to other molecules and pull them and kind of surround by water molecule, and that's what we call how other molecules dissolved in water, and that's for chemical reactions is very helpful to occur.
Okay, so and I another idea that I just want to throw out there is it's also been critical for any life to have thrived here on Earth, and because we know we're here. We're one instance of life we know that has arisen out of a planet, from a planet, and we know that from our own experience, water was crucial to that. It makes sense that when you have one known thing, we're here, we made it, then why not let's look for those conditions elsewhere? And so we limit ourselves because that's the most we know for a fact it can happen. But we don't know about anything else. We don't know whether sulfuric acid oceans or hydrochloric acid oceans would bring all that together. So we look at it in that way.
That's true. And in principle, from that, you can say, okay, water is liquid. That's what we see. Liquid water is great. And what are the liquids? Can other liquids be playing the same role as water? And we say, yes. Indeed, in different environments, other liquids will play the same role. And that extends the definition of habitability beyond what we know. And we should also keep our eyes open to also accept those environments where the other liquids can play the same role.
Right. So anyway, I was looking over some of the chat here, and if you guys want to ask some questions, we're going to be monitoring the live chat as well. And so it's good. Boy, a lot of people are here. This is really great. Let's go ahead and get one here from Ryan Korniloff. We'll go ahead and get started right away. I read that recently that the TRAPPIST-1 star flares frequently and may disrupt the atmospheres of its planets, making life on any one of them unlikely. Can you comment? Let's start, though, by commenting on the TRAPPIST-1 system itself. What kind of star is it, and then what sort of planets are in orbit? Can we talk about that first?
Yeah, we can. Jeff,
I'm waiting for Jeff. I don't know. Jeff, are you there? Are you available?
Yeah, I'm still here. I wanted to respond to the previous question.
Oh, all right. I see Kevin and
chemistry is great.
Go ahead.
Chemistry is great, but the truth is that we want to do more than just detect life. We want to learn from it. For example, we want to be able to do a census of life that might inform us about where we might be headed with our own civilization and life on this planet. And so I completely believe that life exists in many different forms. And I agree with your comment and the callers that said, well, it may be that life is more likely in a different form based on silicon or based on sulfur or other polar molecules. But the truth is, if we're likely to be able to communicate and make some sort of understanding and learn from that, then it's going to be water-based.
Okay.
Just to learn from water-based animals and creatures on our planet, we don't know how to speak parakeet. We still don't know how to speak dolphin. And the idea of communicating and learning from life, which is not water-based, which is going to be entirely weird.
Yeah, I also would like to talk about communication later, about animal communication. I have very anecdotal case to say, actually.
All right, I'll just make a quick note to come back to communication.
Yeah,
okay.
That would be great.
All right.
Yeah.
Okay, good point. So I appreciate that. Now let's go. Okay, so Svetlana, let's talk a little bit about the TRAPPIST-1 system itself. Can you give us a little bit of a sort of a primer on what it is?
Sure. So this is we became aware that about this definition. When we define habitability from the point of view of water, we find out, as I said, the distance from a star is important. So we for the temperature on the surface. So we look at stars of different luminosity, what we call, so it's like different temperatures and radiation levels, and we calculate how much energy comes to the planet, and we find out that this distance between planet and star becomes smaller as we go to less luminous stars, and TRAPPIST-1 is one of such systems found around less luminous star than the sun, and we call them red dwarfs. And we know from many decades of studies of red dwarfs, they're beasts in terms of flares, and many of them flaring like crazy, more active than the sun.
But wait, they are, but that's early in their lives, right? Don't they kind of stabilize a little bit? I mean, first of all, these stars, folks, live for trillions of years, okay? They live a very, very long time, and they're also very cool. But isn't that instability, or the active part, isn't that early in the star's life?
Yeah, it's early, but it doesn't decay very fast for M dwarfs. For solar type stars, yes, it maybe in 100 millions, 300 millions, it becomes much quieter, and after 1 billion, definitely. And in M dwarfs, it's not. They can be still very active, and we don't understand yet completely how this magnetic fields which cause this activity are formed there, and that's why we like to study these red dwarfs to understand it. But we also find out that even later in their life, they're actually pretty active, and flares can be frequent and powerful.
And that's important for life because the TRAPPIST-1 planets are how close to the star? They orbit very quickly, right? In a matter of days.
Yeah, I have to look up.
It's so close that you froze. Oh gosh. You're breaking up, Svetlana. So I will, until she comes back a little bit, hopefully her internet connection will get a little bit better. Red dwarf stars are quite let me just back up a little bit. I went to there you are. Are you back? Are you there?
Yes.
Okay, good. I can hear you now. So I was telling you that these planets around TRAPPIST-1 are actually pretty close to the star, correct?
Yes.
And so that has implications. For one thing, it's great because it means this is a cool star. It's a small star. Liquid water can be present, but they have some pretty funky years, right? I mean, it's only a matter of days these planets go around the star, and they might even be tidally locked, right?
Yes, and the same as for Proxima b, we also discussed that they could be tidally locked because they're so close to the star. It's not necessarily, it's a high probability that they are, but not necessarily. So until we really look at them very closely with our big telescopes, we will not know.
Yeah, but look, the problem is we're looking at these systems through the lens of what we know here. There are lots of reasons to believe, for example, that a star that is flaring a lot of the time has a large radiation environment, that evolution might be accelerated, that the mutation rate
this is also discussed. Absolutely.
So wait a second. You're saying, say that again? Because there's all this activity on a star, the evolution, the mutation rate might be accelerated?
Oh, yeah. Just like we know,
or it could also be annihilated, right?
Yeah, it can be annihilated or accelerated, both.
But remember, the point of evolution is for life to adapt to a changing environment, and so the existence of a high radiation environment means that the life is going to be different. But we have no reason to believe that it means that there isn't going to be life.
Yes,
the
and
other
actually,
feature of these
I'm sorry, Jeff.
the
Yes.
other feature of these systems is that if they are tidally locked, then there are a multitude. There's a continuum of biozones, depending on whether they're at the substellar point, right, with the M dwarf directly overhead, or whether they're at the terminator region where there's this interesting twilight, or they're on the far side where the radiation environment is much less.
Yes, and it can be near the poles as well.
It could be that these sites are the ideal incubators for a diversity of life that we could never have in the Earth, because we basically had fewer bioenvironments, and the diversity in the environment was much less broad. So, look, I think that the speculation that, this doesn't look like Earth is not very well founded.
Okay.
Now, if it turns out that the activity of the star is such that it blows away the atmosphere, then, then maybe the life as we know it is harder to evolve. But even that's not a clear argument, because atmospheres are transient. There's sources of atmospheric gases that are taking place, as well as the radiation and the chemistry, which is doing the opposite. It's degrading the atmosphere.
So Ryan Korniloff, that's directly answering your question about the habitability. Oh, we lost him again. About the habitability of TRAPPIST-1 and atmospheres being stripped away. If I understood Jeff correctly, Svetlana, did he just say that atmospheres are continue? They can be stripped away and then come back again? Did I hear that right?
Well, yes, in principle, sure, it can be stripped away by strong radiation and ionizing radiation, and also particles and stellar wind. But then it can recover itself from outgassing if the rock is still hot, for volcanic activity and so on. So that probably happened several times also on the Earth.
Well, wait. In the case of the Earth, the atmosphere that we have now is nothing like the primordial atmosphere. For example, you go back only 1 billion years or so, and you end up with an atmosphere which has 1,000 times the carbon dioxide that this Earth atmosphere has. And it's
because it was mostly outgassed. Yeah.
This atmosphere of carbon dioxide has been captured into carbonates and life forms that are, for example, limestone. So the atmosphere is a transient thing, and even the existence of a high radiation environment doesn't mean that the atmosphere is necessarily not going to be there. And the thing you said earlier is also important, which is these are stars that live for much, or will live if they could, lifetime of the age of the universe.
Yeah,
and so
trillions of years.
Yeah, the opportunities there.
So Jeff and Svetlana, let me get a comment from you. I went to a talk with Dave Charbonneau a long time ago, and he said that he thinks that red dwarf stars are the best place to look for life in the universe, as far as the type of star that would probably harbor life. Do you guys, first of all, do you agree with that statement? And why do you think that might be?
Well, I don't think there is a best place or worst place. I think that we define it somehow. We always limit our definition. Like we say, okay, we want water, or maybe we want not water. Some people say on Titan there is liquid methane and ethane on the surface, and that could be a different life there. So what's the best? This definition is quite relative. But yes,
I think the reason he said that and where he's coming from there is that red dwarf stars are the most numerous in the
abundant,
sky.
yeah.
They live for so long. The chances of them having planets that might be favorable to life is actually pretty high. So it makes sense to start our search there, right?
Yes, in this sense, I absolutely agree. And as Jeff said, we can find some different forms of life, not necessarily like ours. But also in our planet, we know that there are organisms living in high radiation environment and thriving there. In nuclear reactors, we find life. And, this life is just something very, if it appears, it's hard to eliminate, I think.
All right. Jeff, what do you think of that comment that Dave Charbonneau made about red dwarf stars? Anything to add to that?
I think it's really hard to inform where we should put our energy to find life, except on the basis of this ansatz that if we're going to communicate with it and learn from it, then it's most likely that it's going to be water-based.
All right, I'm
So
getting from both of you, stop putting limits on stuff. Let's just
Yeah,
go out and look for it.
For
Okay.
example, Tony, I think that there aren't any planets except ours in the solar system. I've been taught as a graduate student that it's really, really hard to form planets, because just look around and we only have this one solar system. We haven't found them. So I'm going back 25 years.
Right.
25 years ago, we said, gosh, planets are rare. Planets are incredibly rare. It's hard to have a circumstance that would create
That's
planets.
true. We were the only solar system in the known universe.
No, I would in graduate school. That I remember a conversation with Martin Schwarzschild. Right, he was teaching a class in stellar dynamics, and this conversation was about, well, what do you think about whether or not planets form as? I mean, we know binary stars are as common as single stars, so maybe there's a hint there that complex systems happen, but what we believed and what was discussed was, well, it's unlikely that these low mass systems would be unstable. They'd be propelled out of the evolving solar system. So,
but I want to say that
every time
we must be sure we find something which we didn't expect. So that's my statement about it.
Right.
Where we should discuss look for best or most unexpected result, I don't know. But,
all right. Well, let's go. Let's talk about the.
Sure.
Go ahead, Jeff.
No, I'm just putting out some shameless commerce here.
You're doing some what?
I want you to see some of the exoplanets that we've discovered here in Hawaii.
Oh.
They're very small.
Yeah. And they're on your desk. That's great. All right. Well, let's talk about some of these. Now, what you got there is the ExoCube. That's one of the things you guys have been using to raise awareness on exoplanet research and also to raise money for getting these telescopes built. And in there is a map of 50 of the closest exoplanets to us. So of those 50, that's what we want to hear to talk about. What I want to ask both of you is, of those 50 exoplanets, are any of them looking more promising to you than others, or are they all equally promising as far as harboring life?
No, they're not equally promising. So I must tell that some of them are actually like Jupiter size, and what we hope is that they have moons, and those moons can be habitable, because this whole system could be sitting in a habitable zone. So that is also another opportunity. So some of them are giant, some of them Earth-like. So again, what's your bet for the moons, for the Earth-like planets, for super Earths, or for smaller Earth-sized planets? So that is difficult, actually, to say.
Okay. So I'm reading some of the comments, and there's one here on, I just read the comment, and Jeff, if you want to comment back, that's great. This is from Attila Jacobi. He's saying, Dr. Kuhn, I listened to a few talks you held about the Colossus telescope and the consensus of life on the closest exoplanets based on waste heat produced by technological civilizations. And he's asking, can you please explain how we know the difference between volcanoes and cities on other planets?
Right. That's a good question. So the idea, and Svetlana's talked about this, and there's a paper that shows how we can actually make an image of the heat distribution on a planet from the rotation of the planet, and then infrared observations of how the brightness of the planet changes as it rotates and as it orbits. And your question is, well, we know that planets have other heat sources besides us. How would we be able to distinguish, say, the volcanic distribution of, say, an earlier Earth that has a long distribution of heat? And the answer is that in some cases we could be fooled. But the important ingredient of life is that the temperature isn't very different than the ambient temperature, right? Our metabolism needs a temperature a few degrees above ambient to be able to stay away from the equilibrium that makes our bodies work. Volcanoes and geothermal things have a temperature which is often much, much larger than the ambient temperature. It's different physics that creates it. Life evolves in such a way that I think we could, with very general arguments, see that life temperatures are slightly larger. the waste heat that cities produce is maybe a little bit hotter, but in general, that waste heat that we generate is close to the ambient temperature. So the way to distinguish, so suppose we use this rotational imaging technique with our big telescope to make a map. We make a map that actually tells us the temperature distribution. And if it's really hot, we know it's unlikely to be related to life. If it's cooler, but still above ambient, then it's possible. It's not a proof, but it's much more likely that it's due to life. And then we look at other things. We look for biomarkers in the atmosphere.
Okay, when you talk about waste heat, though, let me just clarify one thing. Are you talking about our waste heat bodies?
Yes.
Well, that's part of the waste heat. Remember the Matrix? In the Matrix, the story was about how bodies were used to generate energy, and that's not an insignificant amount of energy. People talk about, well, if you're looking at an exoplanet, should you look for example, lights, nighttime lights? And you've all seen pictures of the Earth at night. And the answer is probably not. That's not very much energy. There's much more energy in the infrared that's produced by all of the power that we use. So anything that consumes energy and does work eventually produces heat, whether it's your cell phone or your car or a computer or your body.
Actually, air conditioning produces a lot of heat.
Yeah, the net signal, the net energy of an air conditioner is positive, right? It locally produces something that's cold, but the overall energy budget of an air conditioner is that it produces heat. If everybody used an air conditioner, we'd make the planet hotter even faster.
Yeah.
So the waste heat is we call it a thermodynamic signature of life. Right now, humankind uses 0.05% of the total power that the Earth intercepts from the sun. That's a remarkable number because it means 0.05% of the solar radiation that strikes the Earth is converted into heat, and we can't escape it. All of our the use of coal and oil and nuclear power ends up as heat, and we can't get away from that fact. That's an inescapable global warming problem that eventually will be a clear indication of life than other sources of heat. So all of the heat that is created, or the power associated with photosynthesis, is even larger than the energy that we use as a civilization. And that's also another signature that we could find as the biomass thermal distribution.
And it's more than just... Go ahead.
Yeah, go ahead.
I was just going to say it's more than just heat, though, isn't it? I mean, we can also look at other gases in the atmosphere spectroscopically. I mean, we're trying to do this now with Hubble and other telescopes, where they're looking at the light as it goes through the atmospheres of these planets to see if there are biosignatures in the atmospheres of the spectrums of these atmospheres, things like methane and things like that. Correct. So we can look at more than just heat to see other signatures. What would some of those? What would some of those be? Go ahead.
It's necessary to combine these different signatures because there will be always confusion, and in science we always kind of try to get the same result with different techniques, and after we get it several times we say, okay, that looks like life, and it will take some effort. What I also like about this waste heat is that it's escapable, as Jeff said, and unavoidable, and it doesn't depend what they're doing. And so this means that we actually can find those civilizations independently, whether they want to be found or not. So we will not ask them. We will just find them.
Okay, well, I want to go back to a simpler topic. Let's forget civilizations for a minute. I mean, that would be great. But what about just basic... just regular, like super, I hesitate to use the word simple, because I got in trouble for that once. Bacteria, things like that aren't necessarily simple forms of life. Yet, there's evidence that they've been on Earth for as long ago as 3.5 billion years in Earth's history, perhaps even longer. That's almost right away. I mean, the planet formed
Yes.
And suddenly, not too long after, there is organisms on this planet. And
Exactly.
so what about finding those? And you're talking about waste heat. They're not going to have a lot. But is there ways? Well, Jeff just raised his eyebrow. At least I don't think they will. How would we find, or can we find, that kind of life? To me, that's pretty significant.
Yeah, we can find them, and I'm working on this biopigment story. So this is all these organisms. They contain special molecules which interact with the light, and like basically be thermosynthetic or photosynthetic, like using the heat, or this, which means infrared radiation or optical radiation for maintain the chemical processes in their bodies, and these molecules can be detected spectroscopically, and if these biopigments, or even the bacteria as a whole organism, get into the air, we can even find them in the atmosphere, and that's what we do study on Earth. There are airborne bacteria, as we know, and flu bacteria all over. Flu viruses we have, and different kind of bacteria. But also in the air, simple bacteria there, not necessarily pathogenic. And so
you're saying that by looking at the pigments and basically, would that be albedos of different areas?
No, that is a spectrum. You have to look at the spectrum. Yes.
All right.
The spectral signature.
Sorry, I still got my head on around those albedos we talked about last week. So.
Yes. So it's a different technique, but it's a strong signature, because those pigments, they evolved in this organism to capture as much as possible light, and they have very specific shape, like chlorophyll and carotenoids. Very, very specific, like almost box shape absorption bands, to make it really efficient for the organism to capture the light.
So another way of saying that is that almost all of the colors on Earth are caused by life of some form or another. We can think about pigments that are generated by minerals, and there's some diversity in that. But the colors and everything that gives the surface of the planet color is related to life. And so just by measuring the color or the color distribution on a planet, you've got to think about life.
Mineral colors also can do some be bad friends of us, like how we say wrong friends, or how do you say that?
Right. Right. But it's very difficult to imagine a process that yields a planet which is entirely sulfur, for example. Right.
Yeah, or entirely olive. Yes, it's true. Yeah.
And so it's the color and the diversity in the color of a planet, which is another hint. But Tony, I think what we're saying is that what we have and what we're trying to develop is a toolkit for indicators of life. And no one of those indicators is probably 100% certain. But as we apply the infrared information, the temperature information, the molecular band, the narrow band spectroscopy that we can begin to do on exoplanets, all of that, I think, is how you build a case for life.
If you classify it, it's all about molecules, basically. So you can say simple molecules, these are gases, product of the life, oxygen, one of them, although again, it can be organic or inorganic oxygen produced. Methane the same way, and again, if you find oxygen, methane, is not necessarily life is there, but there is at least a hook to study more. And then more complex molecules related to intelligent life, molecules related to like biological processes. So this is all basically about molecules, finding specific molecules there.
Okay, I want to pick up on Jeff's point about toolkits and finding life and what we're going to need. It's interesting to think about all the different ways in which we're going to need to make these detections to find out whether life is on a planet or not. But I'm getting some comments in the chat section here about instruments, and one of them was a question about, do you guys think the James Webb Space Telescope has a chance of discovering life? And another has to do with the 30-meter telescope.
No.
Oh, we were pretty quick on that one. So you're saying no to JWST.
Small, yeah.
No. James Webb is too small. Well, it has two strikes against it. One is it's a telescope designed. We got to get astronomers away from thinking that telescopes are general purpose instruments that collect light. I mean, that's what drives us to build bigger and bigger telescopes, and then we try to make them diffraction limited to see through the atmosphere. But that's not the biggest problem when we ask, can we see the light of a faint planet that's 1 billion times fainter than the nearby star? So it turns out that the advantage in measuring that light gets better, like 1 over the diameter of the telescope to the 4th power. So if you can make a telescope that compensates for the atmosphere, and that's one advantage of going to space, you don't have an atmosphere. But nowadays, we make telescopes with adaptive optics that are diffraction limited and that perform, at least in terms of their resolution, as well as telescopes in space, or they can with very careful, what's called adaptive optics. And if you double the size of the telescope, that means that you go from the James Webb telescope is what, 6.5 meters?
Yes.
The largest telescope on the ground is the Keck telescope, which is 10 meters. And even when we have the James Webb, the Keck telescope, with the proper adaptive optics, in principle, should be, what's the ratio of 10 over 6 raised to the 4th power? It's something like 10 times better on the ground. Now, it's still 10 times better, but it's not the best way of doing this, because the Keck telescope, like the James Webb telescope, is made from a whole bunch of little mirrors that have to fit together, and so they have to make an optical surface, and their edges are controlled by electronics in a way that scatters light. So it's not an accident that all of the direct detections from the ground of exoplanets, essentially all of them, there are a few exceptions, are done by single aperture telescopes like Subaru.
Or VLT.
Or VLT, right? Subaru and VLT,
Or
which are big, or Gemini. They're 8-meter single mirrors that are not cracked up into a whole bunch of segments.
So even Keck is hobbled a bit, right, by this diffraction.
Oh, yeah, Keck is the world's largest telescope, but it's not really the telescope that you build now to do the exoplanet problem. We have to get beyond the Keck era of telescopes. And the Keck era of telescopes includes Keck, it includes the extremely large European telescope and the TMT telescope, and also the space telescopes.
Right, and so I've been pretty active in talking about the space telescopes. There's a lot of plans after JWST and after WFIRST to go into talking about these very large telescopes that are going to be built up in space. Almost all of them, though, involve this segmented mirror design that you're talking about, just bigger JWSTs. And you're saying they're hobbled pretty severely by the diffraction effects of all these segments being but curved into a single, or try to be curved into a single optical surface. Well, what about? Go ahead.
I was just going to say, it's not their bad telescopes.
No, I know they're not bad telescopes.
faint objects. Even LUVOIR, right? This telescope that might happen in 25 years with NASA is only about the size of the Keck telescope, and it's these many segments.
Yeah,
it's a bit bigger.
The exoplanet problem they're talking about, and the detection of life. I'm 99.99% sure is going to be done on the ground from the Earth, not from the sky, because of this huge advantage that the diameter of the telescope has, and the possibility of making telescopes in different ways here on the ground.
What about the way they're operated too? Space telescopes are operated on a time allocation basis. You apply for time, you get approved based on your science, and then they say, okay, yes, we will look at this object. Ground-based telescopes also have a time allocation committee, but they're able to run in sort of a survey mode as well. And by survey mode, they can look at large areas of the sky for a long time and make discoveries. I think that's pretty important because, for the dark energy survey, for example, using the Blanco telescope, they're able to look at 5,000 square degrees over 500 nights, and they can see a lot of stuff in there that a space telescope is never going to be able to see. So how important is that?
Well, but wait. Hubble had a campaign that the deep field. Right. I think Svetlana was going to say the same thing. And that the Hubble Deep Field spent lots of orbits staring at a little tiny
I know all about
size.
I know. But that wasn't a survey. That was a tiny patch of sky, and that's not the same thing as a survey, is it? I mean, it's
well, we're in violent agreement.
All I'm trying to get at, Jeff, is the mode of operation of a space telescope doesn't lend itself well to these random discoveries that we're talking about.
Absolutely, you're right. And the scale of the financial investment in putting a telescope in space, even if you could make the mirrors really big and they didn't have to fit into the fairing of a rocket, the scale is a factor of 100.
Yeah.
So if Planet's Foundation generates $100 million or less, we will build a telescope that's dedicated to exoplanets. And that's the other part of the picture, that if you build the telescope to match the problem that you're trying to solve, you can solve that problem in a much shorter period of time and much more powerfully than you can using a telescope that's designed to satisfy the great mass of humanity, that the astronomers that want to use it to look at.
I couldn't agree more,
galaxies.
But you also know that in order to get these telescopes built, they have to have a large user base. You don't want to. You don't always have $100 million for.
Wait, that I'm not in violent agreement over, because the world's largest telescopes, every single one of them, if you go back 150 years, have been built by private foundations or private individuals and small groups. So the Yerkes telescope, the Mount Wilson 100-inch, the 200-inch Palomar, the Keck telescope, those were at the time.
Interesting point. Actually, I hadn't thought about that.
And they weren't built by the National Science Foundation, and they weren't built by the National Astronomical Observatory of Japan. They were built by essentially individuals.
Okay.
And that's how we're going to do the exoplanet problem.
Okay.
Yes, and in principle, you say you need a bigger community. I think we have a whole humanity behind us. Everybody wants to know if there is life beyond Earth. So that is the biggest community ever to answer that question.
Good point.
Isn't it?
Yeah, I don't think anybody doesn't want to know the answer to that.
Yes.
Okay, well, I don't want to drive this all by myself, especially when I've got good comments here. Talk a little bit. There's some questions about the TMT. People are asking about that. Do you guys have an update on it? What's going on with it? Is there a problem with it? I thought it was doing all right. Do you guys know anything about the TMT?
Sure.
Sure.
Jeff is in Hawaii. He can answer that, I guess.
So I think we need the TMT for all of astronomy except exoplanet studies. So there's a huge community. But it's become, I think, not clear. The TMT organization, for example, has officially designated what they call their backup site in the Canary Islands. And it's going to complicate the TMT if they don't get a permit from the local community in Hawaii to build. And that's a process that drags on.
And that permit has not been secured? I was under the impression it had.
No.
It was disproved. It was granted and then disproved. Sorry to add this.
Okay.
The process is ongoing and it will be in the courts, but it costs money, and I think the TMT organization is hopeful, and as everyone in Hawaii is hopeful. Okay. But it's unclear.
All right. So Gabrielle Dema is also commenting. TMT is looking at alternative sites. The Canary Islands are a strong candidate. They will start construction either in Hawaii or the Canary Islands by April 2019. I had heard that too about the Canary Islands. So that's true. Larry Keese is commenting. Tony, we had a great presentation from the Dragonflies telescope. That's right. We did have a hangout on the Dragonfly telescope. That would be on one of the previous hangouts. Joseph Parker, I guess it's easy to be overly simplistic when deciding which star systems are likely to produce life. In other words, we may well be in for some big surprises as time goes by, if I'm understanding. And that's right. And if you listen to Svetlana and Jeff, both of them are in agreement that we shouldn't be saying this type of star is better than anything else. Let's not limit ourselves. And I guess I tend to go. I've been trying to go towards, well, where are we most likely to find things? And I guess these guys are saying, well, you don't want to really limit yourself like that. So,
well, we definitely have to look at closest planets because we have more light from them. So this is where we start, closest planets. And that's why we create this cube. This is as close as we can go, 50 light years, with our projected telescopes. And we know 25 now candidates. There will be more, and we'll look at all of them.
And you guys, I guess, won't give. I asked you if you had a favorite that you would like to, a favorite candidate among those 50. Anything?
Well, Prox B definitely is the closest one. I'd like to find more planets in Alpha Cent system. I want to see planets around Alpha Cent B, A and B, because then this is a chance to see so many planets if there are any of those, and there must be. There is no limits on gravitational perturbation. I mean, there are, of course, but there is a condition. The conditions are good for planets to exist there, even though it's a binary star.
Okay, and Jurek Mazino has a good question that I'd like to bring up as well. What are the chances of us finding life on an exoplanet before we find life somewhere in our own solar system, like Europa? We haven't found evidence yet, and we have landers on Mars. Any comment on that?
Yeah, we just discussed it last week with Pete Warden, and there is a live chat recording on our Kickstarter page. And we agreed that it's 50-50 because we don't know.
The race is on, right? Okay, and Larry Keese is like, please sign me up for the imaging analysis team of citizen scientists. Yes. And you guys have a way for people to get involved with citizen science yet, or is it too early?
Yeah, we have some. We work with amateur astronomers actually, with the help of the Searchlight Observatory, and they observe transiting planets. We formulate science cases. We work together with them, and if somebody wants to join, that would be great.
But Svetlana, something that we should think about doing is to synthesize an exoplanet light curve and just put that out there and invite this broader community to figure out what they can learn from that light curve, because that's the basic data that we're going to have. Yeah. And developing those algorithms is something that could involve.
Exactly. I want to yeah. Sorry.
That's a great idea.
Go ahead.
I think it's a great idea.
Yeah, I did this stellar imaging before, and that was a standard actually trick to do. You send, and I know that one of the founders of this technique as well in stellar imaging, Steve Vogt, who built actually a high-res spectrograph for Keck and also discovered lots of planets there. Colleagues made a kind of practical joke on him. They generated this bunch of data with the star which contained the name, his name in letters, VOGT. So, and they said, look, Steve, this is the data we just got from the telescope. Look, apply your method. Let's see the star spot distribution. And he did inversion and found his name on it.
Okay, so Connor Woodward is asking, hey guys, what do you know or speculate about KIC 8462852, which is the star that has huge spikes in brightness, changing as much as 80%. Will the Planets Telescope aim at this system?
Well, that's pretty fine system, but we can do transit monitoring, yes. And we actually observe it also in polarization. We're still looking at this data. It's very distant system, and there is interstellar polarization there, but we wanted to detect if polarization vary with those eclipses as well. So this is still in progress.
Okay. Alexis Desblend is commenting, no Galaxia. That's true. You have to think she's in the Netherlands, and it is now, I think, it was 1 o'clock when we started there in the morning. So I think she's probably not going to be up for this. This is our latest one. Pete Kuhn's, hello from Indianapolis. There's no life here. Beam me up. Okay. Oh, Kevin, I wanted to check in with you. Were there anything from Twitter and or Periscope?
Can you hear me?
I can hear you, yes.
I think you're doing a good job fielding all the questions. The extra ones.
Okay, good. So the just going to go through a few more, and regarding Alpha Centauri A and B, this is from Attila Jacobi again. Currently, they are close together, as seen from the Earth. When will they be far enough from each other to give us a realistic chance to find more possible Earth-sized planets?
Yeah, they come in closer now, and at some point they will separate again. I think the furthest again, they will be like 2050. But before they get there, we still have a chance to study them. This is not of course, it's conditions not perfect, but we still can study those systems, those stars.
Pete Kuhn's is commenting, where are the billionaires to fund a dedicated life-searching telescope? Come on.
Yes, guys, right. We need you. Come on, we need your help. Find those billionaires. Send them to us.
Well, now wait a minute. Wasn't was it Paul Allen? Didn't he get involved in one of the SETI projects?
He funded the Allen telescope already.
Yes,
there you go. That's right. So there's one out there. Oh, there's Galaxy.
Oh, there's more than one. Yuri Milner has committed hundreds of millions of dollars, not only to search for life, to send or to do at least this first study to see whether it's possible to send a star chip to the Alpha Centauri system. But also he's funding the dialogue to understand how to push forward the science of looking for life. So he's a very good example of a multi-billionaire who is spending hundreds of millions of dollars to advance the subject. And that's an important point because historically, the studies of exolife have been funded not by the federal government. The Proxmire Golden Fleece Award put an end to NASA funding of the search for extraterrestrial technology, or intelligence, as we say, decades ago. And so the reason why you're seeing these private efforts is because the governmental efforts are for some reason not really understood or respected. Maybe it's our general phobia in our new political system of aliens of any kind.
Yeah.
So,
develop a new phobia, yes. And concerning this funding, again, to those who listen to us, who will watch later, the practical contribution, please tweet about us, write about us in your blogs, advertise our Kickstarter. We're 19 days to go, and we still hope to collect more donations, and this will help us to finish planets and start with ELF, Exolife Finder.
Yeah, and Kevin, why don't you tweet that out using Exolife and on a link to getting there. Also, if you can do it on Periscope, that'd be great, or maybe even Twitch. Martian Colonist is welcome, by the way, to our. I haven't seen you in a hangout before, so it's good to see you here.
There is one.
There is one, Martian. But I'm going to read his comment. I'm going to read the comment, but I don't get it. So hopefully you guys will. Barstow et al. 2016. Concluded that 30 transits of TRAPPIST-1 would enable Earth-level 03 or 3 detections in planets C and D.
Yeah.
Do you understand that?
So this was,
I don't.
Yes.
Yeah. So this was the idea that if you stack, this is transit observations. So if you have enough transit observations, you can collect enough photons during the transit to hopefully do spectroscopy. Now it was a really big telescope in that estimate from Barstow. I can't remember what the telescope was. But
I think it was European Large Telescope.
Was it VLT?
ELT.
Yes, it was probably the ELT. And for transiting observations, that's true. Transiting observations can benefit from telescopes that don't have to worry about scattered light.
Because all they're measuring is, let me just explain what that is. A transit method is when you're measuring the dip in brightness of a star as a planet moves between the star and the telescope. And what you'll see is a tiny dip in brightness, a very small dip in brightness due to that passing transit. That's what a transit is. And what you're saying is that there's enough of them, you can get spectroscopy out of that?
Well, they're periodic, right? So it's every roughly 10 days, I think, for the habitable zone planets in TRAPPIST are what, D, E, and F. I've forgotten.
He was saying C and D.
and maybe C and D.
The closest one, too.
And so what's the period? It's a few days.
Yeah.
So if you time your observations to synchronize to when they pass across the disk of the star, then you can look at how much the light changes as a function of wavelength, and you can in effect make a spectrum of just that little bit of light that passes through the atmosphere.
Hang on, Jeff. You're saying that if you look at a transit in one wavelength, you're going to get a certain light curve. You move it over a little bit, you're going to get either a bigger or a lighter, a smaller dip based on the wavelength you're looking at. Can you really see that difference?
Yes.
Yeah, sure. That's an
this
established
is how water
way.
was detected in some planets already, in hot Jupiter.
Awesome.
Yeah.
I did not know.
Yeah.
I love this hangout.
But-
I'm learning all kinds of cool stuff.
But here's the issue with that. It takes a really big telescope and lots of telescope time dedicated to all those transits, and it's certainly going to be one of the programs to do the transit spectroscopy of these exoplanet systems. But ultimately, we're not going to get any information about the surface. We can't image the surface with that. And it's a very inefficient way of trying to collect photons that will eventually tell us what may or may not be going on in the atmosphere. Now, there are other things that complicate this. For example, clouds in the atmosphere, aerosols, anything that is intervening and overshadows the spectroscopic changes would make this a harder thing to do.
Yeah, clouds are really unpleasant. If we
In so many ways, in just so many ways.
they are. No, they love the sunshine. You imagine all those creatures over there. They may also love it. So yeah, maybe we see like a Venus-like planet, and should we go to the next one? We'll see. Look for the planets without clouds.
I love that. Clouds are really unpleasant. Well, a couple of comments later, a Martian colonist clarified. He said JWST transits. So I think the paper might have been on JWST transits. I'm not sure.
All right.
Okay, so let's see here. Galaxia, you made it. That's amazing. Let's see. So all right. Well, we are 5 minutes past. I should probably wrap this up, but I want to make sure I'm not missing anything. And Galaxia is saying, I live in the Netherlands, but I'm Belgian. Hi, Germany. Greetings from Belgium. I'm amazed you made it, Galaxia. You must be, it must be early in the morning there. That's amazing. So thank you for taking the time out to join us. Martian Colonist is commenting, Mazenot, or Uric Mazenot's subsurface life on Mars could be one explanation for occasional methane outbursts. Underground life on exoplanets could also produce biosignature gases. I want to leave you guys with one question while we're on the subject of life in the universe, and then I'll look one more time at the chat. I ask this question to everybody because to me it is paramount in finding life in the universe. I think that in order for life to be rare or common, forget about all these the exoplanets that we're talking about right now. If you have a planet, a primordial planet full of all of the right ingredients, the soup, as we always hear, this primordial soup, it is full of things that are constituents of life, but it isn't alive. It's just a primordial soup. How hard of a step, and I know I'm just asking your opinion, but I want to know it. How hard of a step is it for that primordial ooze to go from being not something that's alive to being alive? Do you think that step is easy, or do you think it's hard? Because to me, it speaks on the question of life everywhere. If that step is super hard, then we may never find life anywhere. But if it's easy, then it could be in any place we look. Any comments on that?
Yes. It's not so easy.
You think it's hard?
No, I want to say it's not so simple. The question is too simple here, because what is coming to now to understanding is that life is some kind of a way to mitigate the disequilibrium and maintain this disequilibrium and create it. So it's all related to disequilibrium. And if that soup is perfectly in equilibrium with the environment, I would say it's impossible to create life. There must be some source of energy in that disequilibrium. So you have to have a soup, everything is available, plus disequilibrium, whatever, gradient in temperature, gradient in in any physical parameter, we don't know, and that will define what is life. That's my opinion.
That's a good answer. I like that answer. It doesn't make me feel any better, but you're saying that if we had some kind of spark in an equilibrium solution, we might be able to get it. Jeff, do you have a comment on that?
Yeah.
Well, so Tony, let me ask you a question then. Why do you think that life is isolated to individual planets?
I don't, and I know what you're going to get at next. You're going to talk about panspermia and the other things, and go.
But let me just make one statement of fact, which is that a really cool place for some kind of biological organism to live is in a comet, and the comets in our galaxy travel over distances which are larger than the mean separation of the distance between stars and the plane of the galaxy. And the time that it takes for this kind of diffusion process that you imagine is really short. It's millions of years. So if you were ever to form life on some corner where this spark or the disequilibrium managed to happen spontaneously, and there are lots of other problems with making life, right? The unlikelihood of the autocatalytic reaction that we call DNA and RNA is I'm not a biologist, but I look at the process and I just raise my eyebrows and think that's God, that's magic. But it isn't, again, because we think that we're special. And I think we haven't really begun to explore and understand that life could very well be this very robust and universal and transportable thing that happens a lot more easily than we think. It has
to happen somewhere, and to happen, it has to have disequilibrium, and from my point of view, and if it happens, it has to go all over. And we're maybe super optimistic here, and I believe life should be all over.
I agree that once it exists, it's very tenacious. It can exist in all kinds of places. It can exist in hydrothermal vents in the deep ocean here on Earth. It can exist in the tail of a comet. But it's already there. It's already there. I want to go somewhere that spark happened that Svetlana was talking about. And I think, my hunch is, that is not an easy thing to do. You can't just do this everywhere, where you just have all of the right ingredients but no life, and then you have life. That step, whatever it is, and I've talked to evolutionary biologists. They are great at telling me what happens once life forms, but they don't tell me much about how hard is it. They have nothing to say, really, about how hard that step is. And so I don't think the question is too simplistic. I think that Svetlana, you basically answered it. You think it's hard. You think it's not a common thing. And I'm inclined to agree with you. I do. And I agree with you too, Jeff. When you see it out there, it's going to be all over. It's going to be in tails of comets and all kinds of things.
So I have an exercise that I think we should all do at night when we go to bed. We tell ourselves two things. I'm not special. And I live in an optimistic universe of infinite possibility.
Fair enough. That's a good way. I think that's awesome. Yes, that is a good way to put it. We are not special, and I learned that from the Hubble Deep Field. So I'm just going to bring that around full circle too. Okay, Michael Jobin, it's good to see you. Thanks for joining us. Great guest, Tony. By the way, do you guys have to go? I'm just cleaning up a few things. You give me just a few more minutes. I know we're past an hour.
That's okay.
And then we'll go. That's a good point you said, Brian Hedler. That's a good point you said about comments. I think it could work there too. And let's see if there's any other questions. Kevin, if you see anything, just pipe in. I'm just going to look for any questions, and then I'm going to call it a night.
So I wanted to bring that anecdote about communication with life. We also talk, how we can understand other life, and shall we first talk to the life forms here on Earth and understand them. And there was recently on the news that pet parrot living at home and listening what people do, how they order things on the internet. He ordered himself a new what is called cage, a new cage with the bed.
Oh, wait a minute. Are you sure this isn't an urban legend? It sounds like an urban legend. This sounds like an urban legend.
No. It's a voice. It's our voice control of those device. So he used Alexa and said, "Hey Alexa, I want a new cage," and he heard everything people were ordering with that in his family. So when nobody was at home, he ordered a new cage for himself with the bed.
Wow. All right.
Can you imagine that?
That's amazing. All right.
So they do understand us. Now it's our turn to understand them.
Yes, Svetlana, I know you've touched on something pretty important here. We need to there's so many topics to cover. We didn't even get to the communication, the communication aspect of life elsewhere in the universe, and so we'll definitely get to that. This, I think, was a success. We had quite a few viewers online. I'm going to go back and check the numbers. A lot of good chat going on today, so I think this time might work. If Galaxy is here, then wow, I am impressed. So we're gonna
Martian colonizer. That's excellent.
That's right, Martian colonists. That's right. Thank you for joining. Thanks to all of you for taking time out to comment and interact with us. We're going to be doing this every Wednesday, at least for the foreseeable future. Next week, I think we're going to talk about it, but we might want to go into this idea of communication. Because we didn't really talk much about it this time. And we will maybe delve into that a little bit more. Also, if you guys have any questions or comments, feel free to chime in on Twitter using ExoLife hashtag. I will read those before the hangout starts, and we can ask those as well. So, wow, thank you guys. This was a great hangout.
Thank you, Tony.
We'll see you guys next week. On behalf of my guests, Svetlana Berdugina, Dr. Jeff Kuhn, and myself, and Kevin. Where'd your last name go? Kevin. Lewis. Thank you.
Kevin Lewis.
Yes. Gosh. On behalf of all of these guys, I want to thank you guys very much for watching, and we'll see you next week. As always, keep looking up.
Keep looking.
All right.
Thank you. Bye.
I have to turn off my broadcast now. It's going to take a couple minutes. Okay. I think it's stopping. I think it's done. Okay. We are off the air. All right, guys. Okay. Well, this was good. Thank you, Jeff. You need to center yourself in the camera next time. We looked at half of your head most of the time. So center yourself.
No, the idea was so that you could see the execution.
Yes, I know. All right. Well, guys.